High-resolution mass spectroscopy. This method uses a detector that can measure the mass-to-charge ratio to 4 decimal places. Protons do not have the same mass as neutrons. So a proton is that, but a neutron is this. So we differ in these last digits. 2 protons together have less mass than 2 individual protons. Some of this mass is converted to energy. So an atomic mass unit is equal to 1.6605 times 10 to the minus 24th grams. This is the mass of 1 proton of carbon-12. The periodic table uses a weighted average, and usually for oxygen we will use 16. Let's do this again. High-resolution mass spectroscopy. This kind of mass spec uses a detector that can measure the mass-to-charge ratio to 4 decimal places. It uses the fact that protons do not have the same mass as neutrons. They vary in these last digits. And 2 protons together have less mass than 2 individual protons. The mass of our atoms are measured in atomic mass units, and that's equal to 1/12 the mass of 1 atom of carbon-12. So we look down here, we see the relative atomic masses and abundance of several elements. And these are all out to the 4 decimal places. So carbon is 12.000. Oxygen is 15.9949. And let's see which the other one we use a lot is, of course, hydrogen. 99.99% has 1.078. So we can use this kind of mass spec to distinguish between similar compounds. This compound is a C4H8 oxygen. It has a molar mass of 84. This hexane has also a molar mass of 84. But if we go out to 4 digits, we get a different number. Now, how would we distinguish between each of these pairs of compounds? Well, this first one has 6 carbon atoms. I'm going to have to change my pen. 6 carbons, 12,0,0,0,0, plus 3 oxygens at 15.9949. And we have a hydrogen here, here, here. There's one here, here. I'm sorry, there is not one here. So we've got 6 hydrogens. 0078. And that gives us 126.0315. This molecule has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And it's going to have 18 hydrogens. And we can count those. We've got 3 here, 3 here, and 3 here. That gives us 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If we add this together, we get 126.1404. AMU. So we are able to distinguish the two compounds. Here we have 1, 2, 3, 4, 5, 6 carbons. We've got 2 oxygens. And 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. It gives us a total 1, 1, 2, 0, 5, 22, if I've read my writing correctly. Here we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. And they'll have 3 hydrogens here, 3 hydrogens here, 3 hydrogens there. And so that's 9, 10, 11, 12, 13, 14, 15, 16. And this gives us 1, 1, 2, 2, 8. So by carrying out our calculations this long, we're able to distinguish between compounds that are very close in molecular weight. I want to tell you just a little bit here about gas chromatography. This is usually abbreviated GC. And frequently, if you have a gas chromatograph, you'll put a mass spec on the end of it. So we'll start here and put our sample in here. It goes through a GC column, and various compounds travel at different rates through the column, and so they're separated based on their retention time. They come out, as they come out, an electron beam ionizes them right here. There's a focusing lens, and then they are sorted by mass to charge ratios. Now, a very useful way to use mass spec is to combine the two together. Briefly want to say that they're beginning to do more mass specs of very large biomolecules. These have to be ionized very gently or they fragment too much, and they just end up decomposing.